Okay, I was talking about sort of some prelude to why the atmospheric neutrinos became very important and sort of a topic of subject of intense study. And in that context, I talked about these grand unified theories which predicted that proton decays, but of course, from what we know of, protons have been around since the beginning of the universe, which is something like billions of years. So obviously the lifetime of proton should be greater than the lifetime of the universe, and in fact, based on some other considerations of grand unified theories, it was predicted that the lifetime of proton should be something like 10 power 29 years. They put some other constraints on this grand unified theory, and based on those constraints, one could predict the lifetime of proton, and the answer came out to be about 10 power 29 years. So the question is how to observe proton decay. So obviously you need a large mass which contains, I don't know, 10 power 31, 10 power 32 protons, and you surround this large mass with detectors and hope to catch a proton decay. And the preferred decay mode was proton decaying into, it was expected that this will be the dominant decay mode of the proton. And proton is at rest, so pi naught and E plus will come out back to back, each with energy about 470 MeV. And this pi naught will decay into 2 photons. So what you aim to detect is 2 photons on one side with total energy 470 MeV, and a positron on the other side with energy 470 MeV. And so the problem of detecting this decay mode, it imposed certain constraints on the detector. I will discuss those issues in a minute, but let us take a slight digression and consider this problem from the point of view of symmetries. If you look at the various conservation laws that we know of, from olden times we had law of conservation of mass, and then conservation of momentum, energy, angular momentum, and conservation of charge. But advent of relativity showed us that we cannot insist on law of conservation of mass, because mass can be converted into energy and energy can be converted into mass. So in that sense, instead of having conservation of mass and conservation of energy separately, we have conservation of energy, and in this conservation of energy, we look upon mass also as a form of energy. And around 1918 or so, M.E. Nather proved a theorem which says that for every symmetry there is a conservation law, and for every conservation law there is a symmetry. So we can ask, what is it that is guaranteeing this conservation of energy, conservation of momentum, conservation of angular momentum, etc. And then if we take a closer look, we find that if our theory is time translation invariant, we have conservation of energy. If our theory is invariant under spatial translations, we have conservation of momentum. And if our theory is invariant under rotations, we have conservation of angular momentum. Then we'll ask, where is conservation of charge coming from? What is the symmetry behind conservation of charge? That is where QED comes to our rescue. And I hope you remember from your particle physics course that QED has a U1 gauge symmetry. And this U1 invariance guarantees that electric charge should be conserved. Now, in the last class, we talked about baryon number conservation. Where does baryon number conservation coming? What is the symmetry behind baryon number conservation? Well, you can make up a baryon number symmetry, but it's a made up symmetry. It's not a fundamental symmetry like this U1 gauge symmetry, because if this U1 gauge symmetry is not there, the whole structure of QED breaks down. So you will never ever catch a particle physicist saying that he or she will break this U1 gauge symmetry of QED. But as I mentioned, in these grand unified theories, people have introduced interactions which break this made up baryon number symmetry, and so that is what leads to the baryon number violating interactions, and that's what leads to proton decay. But all this is theory, and in physics the ultimate arbiter is experiment. So what proof do we have that electric charge is conserved, and what proof do we have that baryon number is conserved? So I can't tell you exactly which experiments give rise to these results. I'm only quoting numbers which I have seen, let's say, in particle data book. And if you want to know the more details of these experiments, you should look up particle data book to find out what are the experiments which give rise to these numbers. So, as far as experiment is concerned, you can have electric charge non-conservation at the level of, I don't remember the exact number, but something like 10 to the minus 19. So, in an interaction, if electric charge is not conserved, that non-conservation of electric charge can be about 10 power minus 19 of electron charge. Whereas I should put less than, because nobody has seen a violation of electric charge conservation. So we set an upper limit on electric charge non-conservation. This number is, if not 10 to the minus 19, 10 to the minus 18. It's a number of that order. But on the other hand, the baryon number non-conservation, if we believe that 10 power 29 years lifetime, it should be something like 10 power minus 29, or maybe even smaller number. So, suppose I say that I give you two quantities which are measured, and there are upper limits on these two quantities. Quantity A has upper limit 10 power minus 19. Quantity B has upper limit 10 power minus 29. And somebody, let's say, has given you a lot of money and told you to do some really fundamental experiment. And you are exploring what experiment you will design. And you want to sort of test these fundamental conservation laws and see if you can find any breaking of these fundamental conservation laws. And without any background, I tell you that upper limit on conservation law A is 10 power minus 19. Upper limit on conservation law B is 10 power minus 29. What experiment will you look at? Obviously, you will try to see violation of conservation law A. But as we see here, nobody even dreams of explicitly designing such experiments. What people usually do is they try to push what we call measuring electric dipole moments and magnetic dipole moments of particles to higher and higher values, and as a byproduct they derive this limit and try to improve on it. But this is what we are going to discuss next. Given the predictions of grand unified theories, without hesitation, people started looking for baryon number non-conservation at a level smaller than 10 power minus 29. Why is that? Because of the power of symmetry. This U1 gauge invariance is guaranteeing the structure of QED, and If you give up on UN gauge invariance, you are giving up on QED, and if you are giving up on QED, to some extent you are giving up on whole of modern particle physics. So, nobody seriously thinks that electric charge is not conserved. But on the other hand, people are quite happy to think that baryon number is not conserved, because the symmetry behind baryon number conservation is an arbitrarily made up symmetry. It has no deep physical basis. So that is the sort of important role that symmetry is playing in this, even in our design of experiments, so to speak. So, coming back to the proton decay experiments, you need to, so I have a proton, there is an E plus, there is a pi naught which decays into 2 photons. Now this proton can be anywhere in my detector, and as a rule of thumb, I can only instrument the outer part of the detector. Typically I can't, unless it is there is some enough need, we don't put the detecting equipment within the detector. Of course, modern, in the last 20 years, of course, people are doing this sandwich design, where the active material, detecting material alternate, and of course INO is such an example. But typically we have this big detector and you instrument the surroundings of it, the outer layer. So it means that whatever signal you are catching on the surface of the active material, based on that signal, I should not only measure the energy of the positron, and I should also detect its direction. Direction detection is very important here. And also, timing is also important, because I want to know that this pi naught and E plus, they both start with the time of origin of them is the same. So for which, and mind you, detecting, if you read any book on particle detection, you will learn that detecting a high energy electron or positron is something quite difficult. Because it undergoes bremsstrahlung, it produces an electromagnetic shower. So you have to catch that electromagnetic shower. And if you look at any modern experiment, the electromagnetic calorimeter more or less surrounds, is in the immediate surrounding detector of the interaction point, because this electromagnetic shower dies down quite quickly. So detecting the positron and similarly detecting these 230 MeV photons, that was a big challenge, and it could be solved through this Cherenkov detectors. So 2 detectors were proposed, IMB IMB stands for the three institutions in the US which came together to build the detector. University of California at Irvine, University of Michigan, and Brookhaven Laboratory, National Laboratory. And of course, this is an experiment in Japan, and it's called Kamioka because it was located in Kamioka map. And the idea in these experiments is the following. So, you have a cylindrical detector filled with water, and it's made of a transparent material. The material which holds the water is a transparent material. And it need not be transparent, but then you put your detectors in the water itself. And a charge particle which is produced in the detector, if it travels at a speed greater than speed of light in water, it emits Cherenkov radiation, and it will continue to emit Cherenkov radiation until its speed becomes lower than speed of light in water. So, suppose you have a muon which is produced somehow. How it is produced we'll worry a bit later, but imagine a muon is produced. And that muon will undergo very little bremsstrahlung because of its higher mass. But it is traveling with speed greater than speed of light. So as long as it is traveling, it is emitting Cherenkov light. And at this spot, its speed becomes below the speed of light in water, so it stops emitting Cherenkov light. And you now put photomultiplier tubes all around on the surface of the detector of this water tank, and this Cherenkov light is detected by these detectors. And now if you imagine this whole surface as some kind of sheet like this, if it is a muon, you will see an annulus of light. You will see that photomultiplier tubes in this annulus, they are hit, whereas there will be a dark region inside. You understand how that dark region is coming? Because suddenly the emission of light stops. Imagine if this particle goes all the way to the surface of the detector, then this whole region inside the photomultiplier tubes are lit up. But since the particle stopped radiating here, there is an inner region where there is no Cherenkov light. So there is a darker region inside. So this is how these detectors, they could identify a muon. Whereas if it is an electron, it undergoes bremsstrahlung, and the corresponding photon pair produces, and those pair produced E plus E minus, they undergo bremsstrahlung. So what happens in such a situation is, I have an electron that is produced, but before it could travel any distance, it emits a photon, and the electron travels a little more, it emits a photon like this, and this pair produces and they emit photons. So you have this electromagnetic shower which develops. So the development of the electromagnetic shower, because of this large initial momentum, this electromagnetic shower has a direction. But because of this Bremsstrahlung and pair production, this electromagnetic shower direction is not well defined like in the case of muon. So you find that all the photomultiplier tubes are hit, and you get a signal where the photomultiplier tubes in this whole circle are hit. Not only that, that is one signal, and the second thing is, in the case of muon, this outer rim is quite sharp, because once the muon is produced and starts going forward, that defines the direction, and I cannot have any Cherenkov light if this is the So this is the initial point of the muon, and this is the initial Cherenkov direction, the cone direction. I can't have any hits outside if it is a muon, but in the case of electromagnetic shower, you can have some hits outside also. So the terminology that Kamiokande use is sharp ring and fuzzy ring, and a sharp ring has very high probability of being a muon, and a fuzzy ring has very high probability of being an electron. And I believe this is one of the earliest examples in particle physics where they have constructed a neural network. I mean, nowadays they are called boosted decision trees, but 20-25 years ago they were called neural networks. And so they used these machine learning techniques to identify what is an electron and what is a muon. And I believe they have achieved a success rate of something like 98%. So the correlation between a fuzzy ring and an electron / positron and a sharp ring between and a muon, it's like 98%. So, and this is something, as far as detector physics is concerned, this is something really outstanding, because to the best of my knowledge, this is the only detector. Okay, nowadays the people are talking about liquid argon, but certainly this is the first detector which could detect both high energy electrons as well as high energy muons and make a distinction between them. Because the way, if you read I believe you all have done a course on detector physics and also a lab, and how a muon interacts with detector material and how a high energy electron interacts with the detector material are completely different. So having the same detector to detect both a high energy electron and a high energy muon, it was almost science fiction 50 years ago, and that's what these two experiments have achieved. And so, as you see, based on what I described, the electromagnetic shower of E plus, you can reconstruct the direction of E plus and then measuring catching all the emitted photons and essentially catching all the emitted photons, you reconstruct the energy. And of course, you have to identify the pi naught. The two gamma rays again, they behave more or less same as the positron, but you have to put enough number of photomultiplier tubes on the surface so that you can see the two photons clearly when the two photons come from a 470 MeV pion. The pion mass is 135 MeV, energy here is 470, so the gamma factor is 470 divided by 135, it's about 3, more than 3.5. So the opening angle between the two photons, it's not very small, but it's not very large either. So I should have enough number of detectors so that I can tell that there are two different photons, and so that I can reconstruct the pi naught. So that gives us another constraint. So all these constraints, they put together and constructed these detectors. Here little bit of sociology. IMB, I believe, started their efforts first, and taking into account all the various factors I mentioned, they arrived at a design. But a little later, Professor Koshiba from University of Tokyo, he started the effort to build Kamiokande, Kamioka detector, and he felt he needs to build a detector which is sort of better than IMB, which can do something more than IMB. So one obvious thing is to have better photomultiplier coverage of the detector compared to IMB. IMB, of course, in all these things, money is an important aspect, and IMB did whatever optimization they did, and they decided that if 8% of the area of the surface area of the detector is covered with the photomultiplier tubes, that is good enough for their purpose. And Professor Koshiba wanted double the coverage for Kamioka, and it seems the head of Hamamatsu Corporation was his junior to Professor Koshiba in high school, so he used that connection to persuade Hamamatsu to develop special purpose photomultiplier tubes for the Kamioka experiment, and eventually Kamioka actually had 20% coverage. This proved useful because of this better sensitivity, they could detect lower energy particles, and they could actually detect solar neutrinos with energy greater than in real time. Previous detection of solar neutrinos was by the Ray Davis experiment, But the Ray Davis experiment was designed so that solar neutrino induced reaction takes place at best once a day. And the technique Ray Davis had to collect the argon atoms from it's a complicated procedure. So what they were doing is to collect argon atoms once a month. They expected to collect 30 argon atoms, they collected only 10. So that discrepancy is what is called solar neutrino deficit. But there you are not seeing the neutrinos as they are coming, so to speak. You are seeing the after effect of the neutrino interaction in the detector. But here the neutrino is coming, knocking an electron off from one of the water molecules, and you are detecting that electron. So in that sense, Kamiokande could see solar neutrinos in real time, and they also saw a deficit. So that gave sort of a very impressive support to Ray Davis's observation of solar neutrino deficit. And because of the limited coverage, IMB was not sensitive to this low energy neutrinos. But that is the sort of secondary thing as far as these experiments are concerned. The primary thing for both this IMB and Kamiokande are atmospheric neutrinos. Just to sort of set the stage why atmospheric neutrinos are important for IMB and Kamiokande. Take INO for example. INO aims to study atmospheric neutrinos, but to study atmospheric neutrinos you need this big module, INO module, ICAL module. But before building ICAL module, there is an engineering module, there is a mini ICAL, there is lots of intermediate steps. Why are all these things being considered? And what do these things study? You study atmospheric muons, because eventually what INO will actually study are response of the detector to muons. So we study atmospheric muons in this engineering module mini ICAL ... and fine tune the detector and use that knowledge to have the best possible atmospheric neutrino detector in the form of ICAL. In a somewhat similar way, you can say what these people wanted to detect is proton decay. And an important aspect of detecting proton decay is to measure the energy and direction of the positron. But in order to do that, you have to calibrate your detector and make sure that the measurements you are making are correct. And one very obvious way you can calibrate the detector is through atmospheric neutrinos. We know that these atmospheric neutrinos, they are passing through the detector. Interaction cross sections are small but non-zero, and this is a huge detector. So every day I can expect a few events. So I will utilize those events and calibrate my detector, make sure I can make a distinction between electron and muon. And in the case of electron, make sure I can measure the direction and its energy accurately. And that too, these neutrinos are coming with varying energies. from various different directions. So I have a sort of ready-made source with which I can calibrate my detector. So both these experiments had set up as their first step a systematic atmospheric neutrino study program. By the way, I put Kamiokande-NDE. NDE stands for Nucleon Decay Experiment because the experiment was set up to study proton decay. And by the way, this is again something quite funny, if you can say. This business of, I believe that atmospheric neutrinos actually play an important role in these experiments. Looks like it was realized somewhat late, because when the experiment started, there was only one paper which calculated atmospheric neutrino fluxes, and that was a PhD thesis done by a Russian student, and the paper was published in 1980. And after that, there was no other work. So in some sense, when this atmospheric neutrino study started, in order to compare theory with data, you need an estimate of the neutrino fluxes. But the only neutrino fluxes that were available were by this PhD student from Russia in 1980. So if you look at the older papers, you see a reference to that paper for the next 10 to 15 years. And only after that, I think both IMB and Kamiokande, they set up a systematic program to do Monte Carlo calculations of atmospheric neutrino fluxes. And same thing with cross sections also. The papers that these IMB and Kamiokande they refer to are quite old papers, because all the neutrino cross sections, they are done with neutrino energies about 10 GeV, whereas here you want cross sections with neutrinos of energy 0.5 GeV, 1 GeV, etc. So the difficulty is that at 0.5 GeV, 1 GeV, resonance cross section tends to be dominant, whereas at 10 GeV, deep inelastic scattering is dominant. So you can't quite do the extrapolation from 10 GeV to 1 GeV. So again, a systematic experimental program was set up to improve the neutrino cross section measurements. And as I mentioned, both these experiments, they can make a distinction between an electron and muon, but neither of them have a magnetic field, so they cannot tell whether it is an electron or a positron which was emitted. Similarly, they cannot tell whether it is a positive muon or a negative muon that is emitted. So they put together mu e plus mu e bar interactions together, and they called them mu e. Keeping saying mu e plus mu e bar every time is a bit painful. So in the context of atmospheric neutrinos, when you say mu e interactions, you are talking about mu e plus mu e bar interactions. And similarly, mu mu plus mu mu bar, they are called mu mu interactions. Actually, they are called electron neutrino interactions and muon neutrino interactions. So over years they had accumulated enough data, and they started their run in 1983, and I think by 1986 or 1987 they established that proton decay lifetime is greater than 10 power 30 years. So sort of it was taken for granted that the simplest grand unified theory is not correct. And in fact, I went to University of Pennsylvania to do my PhD, and there was a workshop on baryon number non-conservation, and the keynote speaker was Howard Georgi, who was one of the authors of that simplest grand unified theory, and he commented that, yeah, my senior colleague Sheldon Glashow, who was the co-author on that grand unified theory, he is feeling very down because there has been no signal of proton decay. But of course that was 40 years ago and we are still in the same situation. But when they started studying the neutrino interactions more and more, with more and more accuracy, with better and better statistics, they observed they made two independent measurements, both of which are not consistent with what we expected neutrinos, how neutrinos should behave. One is this double ratio. This is number of muon neutrino events to number of electron neutrino events data divided by number of muon neutrino events to number of electron neutrino events given by Monte Carlo. So if neutrinos don't do anything except behave as given by standard model, as given by the charge current interactions, then what do you expect this ratio to be? Two. No, why 2? 1. See, what is Monte Carlo? Monte Carlo consists of all the physics that you know. And if the data does not contain any new physics, then Monte Carlo and data should match. So this should be 1. But please, rather, expected to be but measured value is about 0.7 with a small enough error bar that we know that it is definitely less than 1. And coming back to say what you said too, so nu by ne Monte Carlo, yeah, we expect it to be 2 because as we discussed, there are 2 muon neutrinos for every electron neutrino, and and the measured value nu by ne data, it turned out to be about 1.4. Now, why am I taking nu by ne? Why don't I look at mu is one data set and ne is a different data set? So why don't I take mu separately and ne separately and look at them? The problem is the uncertainty in neutrino fluxes, and atmospheric neutrinos occur due to interaction of primary cosmic rays in the outer layer of the atmosphere, and primary cosmic rays have something like a 25% uncertainty, which or more than 20% uncertainty, which feeds into the prediction. But when I take the ratio, that main uncertainty cancels out. So if I try to predict number of muon neutrino interactions, there will be a 25% uncertainty, some more than 20% due to that at primary cosmic ray flux uncertainty, and some 2-3% due to other interaction uncertainties. Same is true for Ne. But if I take the ratio Nu by Ne, that main 20% uncertainty cancels out, and I can predict this ratio to something like a 5% uncertainty. That's why in the case of atmospheric neutrinos, things are always predicted in the form of these ratios, so that the primary uncertainty due to cosmic ray flux, which is still at the level of, I don't know what the current number is, but I believe it is like 12 to 15%, it is still quite high.
Cross sections will also be different for neon, neutrino and
at the energy of about, we are talking about energies of about 500 MeV. At that level, the cross sections are close enough. But you are right. In fact, one of my professors at UPenn, who was involved in Kamiokande experiment, he specifically wrote a paper about the differences between muon neutrino cross section and electron neutrino cross section. And his conclusion was that for the energies of interest, the differences between them are small enough. And of course, known difference you put in your Monte Carlo. But of course, there are always uncertainties which also you put in your Monte Carlo. His basic point is one need not worry too much about the difference of the cross section of muon neutrino versus electron neutrino, because when the energy is 500, muon mass of 100 does not lead to that much of a kinetic effect. This is one important measurement they made, and the second important measurement they made is with muons only. They have what they call up by down, or sometimes it is also written as up minus down by up plus down. So what I mean is number of muons going up minus number of muons going down divided by number of muons going up plus number of muons going down. What do I mean by going up and going down? You see that detector is a cylinder, so it has an axis, and the line outward pointing towards the sky. I can take that line, and so I define that to be my positive z axis, and I take a dot product of muon momentum direction with this z hat, and if that dot product is positive, then it is upgoing, and if the dot product is negative, it is downgoing. And so I can measure this ratio also, and here again, since I am taking ratio, the main uncertainty cancels out, and I can make a accurate Monte Carlo prediction of this ratio. And again, if the muons have no funny, are not doing any funny thing, if they have only standard model interaction and nothing else, what is the prediction for this ratio?
0.
Should be 0. But it is established that it is negative. Why should it be 0? Well, you think of Earth, and this is my detector. And where are the neutrinos coming from? They are coming from atmosphere, and as far as our measurements of cosmic rays, primary cosmic rays are concerned, the primary cosmic ray flux is isotropic. It is the same from all directions. And again, to the best of our knowledge, atmosphere is also isotropic. So if the source producing the neutrinos is isotropic, then neutrino distribution should be isotropic, provided the propagating medium is isotropic, but actually it is not because of Earth's magnetic field. See, you have protons coming, they come and interact in the atmosphere, but when they enter the neighborhood of Earth, they are also affected by Earth's magnetic field. And if they are low energy particles, then the effect on them is more. So, you expect some effect due to Earth's magnetic field, but that is only at lower energies. At higher energies, that effect is quite small. So, modulo Earth's magnetic field, you expect isotropic neutrino flux. So, the number of neutrinos coming in like this is equal to the number of neutrinos going like that. So, that is the reason why this up minus down by up plus down, that ratio, the Monte Carlo prediction, we expect it to be half. But the measurement showed that it is negative. There are less number of upward going muons compared to downward going muons. In principle, they should have constructed such a ratio for electrons also, but for some reason I don't remember ever seeing the corresponding ratio for electrons. One should look into that, why that was so. I mean, this I am talking about IMB and Kamiokande. Super Kamiokande, of course, did that. Yeah.
Because we are on, our detector is near the surface of Earth. If you forget the oscillation effects, we may naturally expect more down up, right? Because
No, why?
it's maybe a bit naive. So we have the Earth like that, and on the top side, top surface, we have the detector. Then neutrinos are produced all around the side.
Yeah.
So we are not in the center of the picture. We are
No. Yeah, I agree. But what is relevant here is the solid angle. So. Okay, that doesn't quite look like a, but doesn't matter. You look at the center of the detector, and this is the vertical axis of the detector, and this is the so-called equatorial plane of the detector. Now, you look at things from the point of view of the center of the detector. So, this is the equatorial plane divides the space into two equal halves, and the upper half subtends a solid angle 2 pi, and the lower half subtends a solid angle 2 pi. And your point is that the and what we look at is d square n mu d mu d omega nu, which is d square phi nu d nu d omega nu times d mu d sigma nu d mu integrated over all muon energies. So, what matters is this solid angle subtended at the center of the detector roughly. So, the flux is calculated in terms of number of particles per centimeter square per steradian per second. So that way the upward solid angle and downward solid angle they are the same. I mean, for example, consider a line like this, and consider another line like this. So here you say, oh, here the neutrinos are being produced over a larger area here, but they are being produced over a much smaller area here. But I want the neutrino produced here to go to that single point. So there is that 1 over r square effect. And because of that 1 over r square effect, there is a compensation of this larger area versus this smaller area, and the relevant quantity that comes in is the solid angle, and the solid angle is the same for upward and downward. Okay, so as I have described the basic result of IMB and Kamiokande, that the ratio n mu to ne was noticeably smaller than what they expected, and also this up down asymmetry, which was expected to be 0, is measured to be negative. So both these can be explained assuming that muon neutrinos are oscillating into tau neutrinos as they travel through the earth, but nothing much is happening to electron neutrinos. Mind you, that was only an initial hypothesis. There were that was the sort of simplest hypothesis which explained all the data, but there were other competing hypotheses which couldn't explain the data so well, but which one can't rule out. But by the time IMB and Kamiokande finished their runs around 92 or so, 92, 93, the situation was still quite uncertain. All that we knew was there seems to be something wrong with atmospheric neutrinos. What exactly is wrong, we needed to find out. And that is when the two groups, IMB and Kamiokande, they got together and built Super Kamiokande. And in 98, Super Kamiokande produced such statistically compelling data that there is no doubt it was muon neutrinos were oscillating into tau neutrinos. And we will discuss the Super Kamiokande next week. I should mention in 1996 there was a Golden Jubilee Symposium of TIFR, which was a big affair, and a well-known physicist called Roberto Peccei, who has worked on various different aspects of particle physics and in particular in neutrino physics. He gave a talk on neutrinos. For some reason, he was sort of prejudiced towards what is called LSND. I have not discussed LSND, but there was an experiment called LSND, and he seemed to believe that LSND was correct, and also that solar neutrinos by that time were well established, so he believed in solar neutrinos, and based on it he built up a picture of neutrinos. And at the end of the talk, somebody in the audience asked him about atmospheric neutrinos, and he was sort of a bit dismissive. He said, Well, yeah, I know there is something called atmospheric neutrino problem, but not to be taken so seriously. That was his attitude in 96. But as I told you, in 98 actually, Super Kamioka, which was supposed to study both atmospheric neutrino problem and solar neutrino problem together, but the initial data they got, the atmospheric neutrino data was much more compelling than the solar neutrino data. That was because identifying the solar neutrino signal was a big challenge, which took some time, but by 2001 or so, they had actually, their solar neutrino data also became very good. But it was sort of caused a sensation in 98. There was a Neutrino 98. Every 2 years, every even year, there is a international neutrino conference, and the one in 98 took place in a mountain resort in Japan, where Super Kamioka announced their results. And I mean, people were really amazed by the atmospheric neutrino data presented by Super Kamioka. So we will study that next. We may need the projector for next class. I want to show some figures related to Super Kamioka. I'll mail you a paper so that you keep it ready on your laptop, so we can project, and based on those figures I will explain the physics.
So then this upgoing and downgoing, you said muon neutrinos were taken by Kamiokande. That ratio of upgoing to downgoing, but not for electron neutrinos.
Maybe they have studied, but at least people don't talk about the up-down asymmetry of electrons. They talk only about up-down asymmetry of muons. Maybe if you go through the old papers, somewhere you will probably see some statement about the up-down asymmetry of the electrons also.
Okay, and in Super Kamiokande, that's also mentioned.
Yeah, but Super Kamiokande, as I will mention, it's a much fancier experiment than Kamioka. So they didn't look at up-down asymmetry, but they looked at what is called zenith angle distribution. So that's a fancier analysis. So, and they did it separately for low energy muons, low energy electrons, high energy muons, high energy electrons, and based on that they could conclude that all 4 pieces of data can be explained only by the assumption that muon neutrinos are oscillating into tau neutrinos. Okay, tau/sterile neutrinos, that was their first statement. But if it is sterile neutrinos, then there are the matter effects due to neutral current. Matter effects will come in, and they could rule out the neutral current matter effects, and then they could say it's only due to mu to nu tau.
In these experiments, at first, how did they came up to conclusion that muons didn't oscillate to electron neutrino?
Sorry, I don't understand.
Here, how did they come to conclusion that mu didn't oscillate to nu e?
Well, that is because electron neutrinos are what is expected. What they see in terms of electron neutrinos, electron events, is what they expect from electron neutrinos. So, I mean, in a sort of very simple fashion, the measured electron neutrino flux is what is expected, whereas the measured muon neutrino flux is less than what is expected. That's why.
And why this has to be true?
Sorry, why? Which has to be true?
Why the oscillations is favored for muons going to tau rather than
Because what I just told you, what we see for electrons is what is expected. So whereas if muons are oscillating into electrons, we should see some difference. We don't see any difference. I mean, there are other wrinkles in that argument. All that we will discuss in the next class.
So in this Kamiokande, they are seeing a deficit in down up going neon neutrinos or antineutrinos.
I mean, neutrino plus antineutrino together.
So actually, because of the matter effects, only one of them will be oscillating.
Yeah, but matter effect is a sort of quote second order. No. Oscillations are the same. Matter effects modify oscillations. But matter effects modify oscillations in a narrow energy range and narrow path length range. Whereas these people are looking at the full energy range, full path length range, and their statistics are quite small. So in that sense, the matter effects are averaged out. The statistics of Kamioka, or for that matter super Kamioka, I mean initial super Kamioka. Right now, for example, super Kamioka is trying to make a statement about matter effects, but they say they see evidence, they rule out no matter effects with a chi-square of, I don't know, 3 or 4, something like that. 3, I think they have a chi-square of 3 or something.
So they are saying that there is matter effects.
Yeah. In fact, they say something stronger. They say matter effect with normal hierarchy.
But how will they know? How are they detecting the matter effects if they cannot differentiate between?
By the statistics of mu plus versus mu minus. Mu plus event rate is 1/3 the mu minus event rate because of the cross sections.
And they can differentiate between mu plus and mu minus events. How? Because
on a statistical basis. If you want, we'll discuss it. The details we will discuss in the next class. But if you try to think about it and try to figure it out yourself.
What I'm thinking is,
I understand the question you are raising, but try to think about it. Write down the expressions and see how things will work out.